was impossible. They said an electric car could never look like, drive like, perform as economically, or ever become as practical at home as cars driven by gasoline-powered internal combustion engines. But not everyone agreed. At energy conversion devices and its subsidiary, the Alvin battery company, we knew all the more what the problem was. And it wasn't the car. It was never the car.
The Achilles heel of the electric car has been there's no battery. There's a company called General Motors, Ford Motors, Chrysler Motors. The whole automotive industry has been built on the very heart of having a gas engine, a motor. And now what's needed, and which we provide, is having a battery, an energy source, which allows the electric car now to be an ordinary engineering feat.
Energy conversion devices and the Alvin battery company have started prototype production of this exciting new battery with all the characteristics to make tomorrow's electric car a reality today. The Alvin battery, in addition to roadside recharging in only 15 minutes, is completely non-polluting, is rugged and maintenance-free, can travel long distances between charges, and is simply the most powerful electric car battery around. And cars powered by the Alvin battery offer much faster acceleration than ever before possible with an electric car. But what is also attracting worldwide attention to ECD and the Alvin battery company is the exceptional range the battery offers. For example, GM's impressive impact car promises to travel 120 miles on a charge. But with current Alvin battery technology, it can go over 250 miles on a single electrical charge. And the next generation of the Alvin battery promises well over 300 miles per electrical charge. What's ECD's secret? Previous batteries for electric vehicles, in addition to not having the necessary performance characteristics, also contain significant levels of environmentally hazardous materials. But the Alvin battery, based on new principles of material science and technology, takes advantage of another more efficient, environmentally friendly, but often misunderstood element.
We use hydrogen as our active fluid, so to speak, for our battery. However, gaseous hydrogen and liquid hydrogen are dangerous. By putting it into a solid, that's what we call a hydride. And by using that hydrogen in the form of a solid, it's safe, it's non-polluting, it solves the problem, and it gives you tremendous more energy, no pollution, and solves the problems that have been holding back the electric car.
Ovshinsky isn't the only one excited about ECD's new nickel-metal hydride battery. The U.S. Advanced Battery Consortium, made up of Chrysler, Ford, and General Motors, in cooperation with the Department of Energy and the Electric Power Research Institute, awarded the Alvin battery company $18 million, its first multi-million-dollar contract, to help develop and commercialize tomorrow's electric car battery today. And since that announcement, the consortium awarded ECD and the Alvin battery company an additional $1.4 million to purchase its prototype batteries, taking energy conversion devices and the Alvin battery company one step closer to commercializing and mass-producing today the electric car technology of the future.
We are an American technology, we are American know-how, we are American creativity. Therefore, what we represent is not only the old America that made America great, we represent the new America, America in the next century, that will lead the world in creating socially useful, necessary kind of products that will be of help to everyone.
Besides helping solve some of our greatest problems, pollution, American dependency on Middle Eastern oil, the economy, we believe there's another reason consumers will enjoy riding electric cars powered by Alvin batteries. They are simply fun to drive.
An electric car is now an idea whose time has come. It is going to be a very large industry. It's going to be the new automotive industry. We provide the battery that makes that car practical, and it will make a
Mr. Stanford Ovshinsky with Ovonic Battery. Let's have a big hand.
Thank you, and actually I wear several hats. Ovonic Battery Company is a subsidiary of Energy Conversion Devices, which is the parent company. And my subject for an after-dinner talk is not to give you a scientific description that will glaze your eyes over, but to try to speak to the things that brings all of us here together, which is a common interest in making our environment livable and in making our society serve its needs to our common interests, not only in the environment, but to other social concerns which I will speak of. And in this case, I'm not just going to represent the battery. I gave that talk earlier today, and I will mention a few parts of that again, and those of you who are there will kindly permit. I will probably repeat that, but I will attempt. I can't tell the same story twice anyway. I never was good at that, so if you'll bear with me, I'll try to tell you why we're here and what the reasons for us being here. And I would like to start with the first slide. Now, can everybody hear me?
Yeah. Yeah.
All right, because I really, I'll use what I call my trade union voice. While we're talking, I spoke on the movie strip there about American, and I unfortunately didn't bring the latest one that showed a lot of other things, but I was moved by this picture, very, very moved, and I hope that you'll appreciate it. This is in Mexico, and here is a woman, a young woman, a Mexican woman, with her child, and what she's carrying on her back as she goes up the mountain trail with others, she's carrying a photovoltaic package to bring electricity to her village, where there was no electricity before. This is an important point. Without energy, and that's really the subject of this meeting, without energy you don't have civilization. You have a gathering society. You have a society which exploits women terribly, for example. You have a society where there's no chances for education. You have a society where people die young out of disease and poverty and starvation. So, to me, if nothing else happened, forget about our affiliation that we have a joint venture with General Motors or anything of that sort. I feel that Iris and I have found a way of expressing our politics through our work, which is that you do not have civilization without energy, and we are to provide that alternative energy, which is safe, which is non-polluting and non-depletable, and will be helpful not only in bringing civilization in every part of the world, but will prevent the most important thing, and that is, well, we're trying to have something that appeals to us because we are fighting pollution. Remember that the biggest pollutant of all is war, and you fight war over oil. You fight war over oil, and it's been like that for many, many years. The Japanese went to war when we cut off their oil supply. We have a deficit, a huge deficit, that of the United States that's over $70 billion that goes for oil. Think of what that would do in terms of social programs rather than cutting them. That's per year, as Iris says. We have inflation because of oil. And as I said earlier today, somehow the economists have a reason to assume that inflation and unemployment in order to control inflation, you ought to have unemployment. And I really recommend that for economists so that they understand how this feels. Now, we're talking then about energy. We're talking about how do you make energy? If it's just a utopian idea that, gee, we want to empty the ocean with a bucket, it isn't possible. You're going to be dismissed as enthusiasts, as people who are trying to do the impossible. What I'm here to tell you is that there's practical, realistic answers to the entire problem of energy. And here I'm starting with energy generation. Now that Vietnam is considered part of the United States purview, I suppose I can show this picture without embarrassment. This is Vietnam. And these are the people now. There are hundreds of thousands of villages and communities without electricity. Not only in Mexico, in Vietnam, in various parts of the world. In India, there's how many? 600,000 villages without electricity and so on. And so it's not a United States problem, it's a problem for the whole world. And again, here are people now that are going to be able to have, and I haven't taken all my pictures, showing children reading in light with rapturous eyes because they can now have some books and attend school and so on. Now, I know I'm speaking to the committed, but I just want to stay again to basics. Deadly toll is found in dirty air cities. We all breathe the air, and we take it for granted, and we complain about it. But for the children and for our grandchildren's sake, I must tell you that the air pollution is a terrible problem. It's a terrible problem, such a problem that when Iris and I were just in Europe, there was a scandal in England because the heat wave had brought out the air pollution to great heights from automobiles. And the fellow who was in charge of that program in Parliament was caught, and they had put out a bill to stop the use of cars for a while, and they caught the fellow who was the head of the department driving to and from a couple blocks in a car where he shouldn't have been. That was a national scandal. It would be a scandal in the United States. In other parts of Europe, as you know, they're blocking cars from going into the cities. Everywhere, pollution is choking the world, and pollution is a terrible problem. When the big three went to lobby Governor Weld in Massachusetts, what did they find? It was the same day that he had issued an order saying, do not drive your cars because it is very dangerous in terms of pollution. And they were trying to convince him that there's no problem with pollution at all. It's like the people from the nickel-cadmium industry. When they heard that I was going to replace nickel-cadmium with nickel metal hydride, they said, Mr. Ovshinsky, Mrs. Ovshinsky, don't you understand? Cadmium is good for you. It is one of the worst carcinogenic materials in the world. So I just want to go on from this to something else. I never thought we'd ever see this day, and this is when, from the Department of Energy, when the Assistant Secretary and I announced a major breakthrough in photovoltaic thin film technology. Now, those of you who live in California take for granted, yeah, there she is. And those of you who live in California take for granted Silicon Valley, and you see that there's a plant now that's being built to build 8-inch wafers, and it costs $1.5 billion. And they say in 3 years it's going to cost more than that, $3 billion, $10 billion. You visit our plant, and I'll show you a picture, and we make photovoltaics, not 8 inches. We make photovoltaics by the mile. We put on rolls of steel, and we just make it by the mile, thin, flexible, multi-layered materials with multi-band gaps. What that means is that there's a talk earlier today where it was shown how the energy of the sun is absorbed at different parts of the spectrum. But we design these materials with a thickness no more than 1 micron altogether, which has 3 different band gaps to absorb the energy of the sun. I want to get back to that. All right, yeah, I'll show you. But I'd like to get back to that if I could. This is a plant that's now in Russia. This is a plant that's now in Russia. Ordinary plant. There's no clean room. There's no billions of dollars. There's a couple people looking at computers, and that's all there is to it. And you're making by the mile. Now, what does that mean? That means that technology, science and technology can serve our society, and that's what I founded our company on. Serve to solve societal problems rather than making societal problems. I'd like to go back to the previous slide. And by the way, the only reason I mentioned earlier that she's got the real PhD in the family, the only reason she does that is she exploits me to make sure that I give the talks, and she handles the slides. I mean, what can I say? I'd like to call your attention to the fact that over here are shingles. These are model shingles, but real shingles. Larry Slominski back there, around here, will be able to show you later some of these, what these shingles can do. I just want to point out that a couple hundred square feet of these shingles will be enough to run such a house. And then when we speak of batteries, I spoke about electric cars today. A battery of this size in comparison to the rest of the house, you can't put lead acid in your basement. You put that battery in your basement and you're free of the grid. You can just charge the sunlight, charge the batteries, and it's there for, if you want to be on grid, it's there for just a standby power, or you can be free of the grid. Yeah. Now, these are actual shingles. People talk about alternative energy being, you'll read it in the newspapers. Alternative energy is not realistic. Because what do you do about alternative energy? I mean, you have to build these huge solar farms, and it isn't going to work. Well, the reason for that announcement, that revolutionary breakthrough, which the Department of Energy called revolutionary breakthrough, was because our group at United Solar, which is a joint venture between Energy Conversion Devices and Canon, a very well-known company in the office machinery business, had gone through had gotten the holy grail of over 10% efficiency, stable efficiency in a large area in a continuous type of machine process. And we thank that was, anybody who wants to eliminate the Department of Energy just has no idea of what real value that group does, especially under Secretary O'Leary, who is a wonderful person. So these shingles look like any other shingles, not a very good picture. I just grabbed something there. And why alternative energy is possible? I know some of you would like to put flywheels in cars. Some of you would like to put windmills on islands. Some of you would like to use geothermal, but you aren't going to put a windmill on top of your house. You're not going to put a flywheel on top of your house. You're not going to put a volcano on top of your house. What you're going to put on top of your house is a roof. A roof, and since you need a roof, then you ought to have shingles, and you can make them in metallic form, for a metal roof, or you can make it as you do here. And therefore, this is the answer. If you have shingled homes all over the world, and they tell me, the National Home Builders Association tell me, Mr. Ovshinsky, you're wasting your time with the automotive industry. We're much bigger than the automotive industry. We're much bigger than they are. Work with us, and we are working with them very, very nicely. Now, I'm not very good at marketing, so I wanted to put this slide up here. It emulates a conventional asphalt shingle in form and function. Aesthetically appealing, which I like that. Blends with a standard roof. Small shadow loss, less than conventional photovoltaics. The module is a roofing material. Additional shingles are not required underneath. Separation of the trades during installation, i.e. roofer and electrician work independently. Very simple to install. With 10% module efficiency, only 300 square feet roof area is needed to meet household need of 3 kilowatt. Now, when I said we're going to make photovoltaics by the mile, when other people were thinking about making them the size of a pen, and that was before we made our arrangement with Canon, people thought that that was impossible. That's the next lesson to learn, that there's always be suspicious of people who tell you that things are impossible. This is now done routinely. That plant has been running, our energy conversion devices plant's been running since about 1982, around the clock, very high yield. In semiconducting language, for those of you, we get about 100% yield. And with only planned shutdowns for cleaning up, it just goes, it's a very, very simple and robust design. I won't tell you what the science and technology is, because that isn't fit for a after-dinner talk. Irish and I were at an after-dinner talk where somebody got up and showed about 15 slides about the function of amorphous, 100 slides, she says, I'm sorry. And we were sitting with a Nobel Prize winner and several other very well-known scientists, and they were heckling the speaker, and I don't want that to happen. I'd like to say then that what we're interested in is a system. Those of you who think that there's just one thing to do to solve the energy problem, you're wrong. You have to have systems. So part of the idea is you want to generate electricity, and you want to do that through photovoltaics. Although we used to have a very successful commercial plant, was also using thermoelectricity. And it was very successful technically, but we never had enough money to really put behind it, and we're going to go back into that area again. But we used sunlight, we used waste heat, and then you have to store electricity. Now, if you're going to store electricity, everything is portable. Well, there is a revolution going on, and all of you have seen the mobile phones, you've seen the faxes, you've seen the desktop, and the laptop computers. All of them that use nickel metal hydride, look for the name, whether it's Toshiba, Matsushita, Yuasa, any of them. All of the nickel metal hydride batteries are made under our patents. And therefore, this battery that I'm going to be talking to you is not a new battery. I invented it years ago. But we put it out in the consumer field where it proved itself very well. Now, I wanted, however, to put it into automobiles. And I must tell you that it's very difficult to convince anybody in those years, including many of my very good people on our staff who really didn't think it was possible. That's a bad word. Now here's a beautiful car. Can I have the other one back again just to show it? Yeah. I just wanted to indicate that that battery that you see there is this battery here, and that you put them in packs, and that the packs then you put into automobiles. Before I leave the photovoltaics, I just wanted, we did this for NASA just many, many years ago, just to prove something. They said they'd like to have something thin and flexible, and you can't do that with a photocell. They're heavy, crystalline, and they break, and they do this or that. And so I did this just we even have an urban model with bullet holes through them. Still works. And it still works. So, again, what you need to do is to understand what the problems are in science and apply the creative powers that we have to solve those problems. And in the storage materials, this is called nickel metal hydride, based on the same kind of physical principles that I use in photovoltaics, but for different purposes. One is for light generation of electricity through light. The other is through the storage of hydrogen in a solid. And yeah, I think we ought to. This is the GM Impact, which is a beautiful car, by the way. And we have a joint venture with Canon for the photovoltaics. We have a joint venture in Russia. We have for the photovoltaics. And we have in the United States a joint venture with General Motors in terms of manufacturing, not research and development, but manufacturing batteries for electric cars. And this was the thing that led to that biggest company in the world, combining with one of the smallest companies in the world, was that we took out their lead acid batteries that was in this kind of case, put in our batteries, which they thought was impossible in the first place, and they were that 120 miles that you saw on the other on the TV, they had gotten down to about 60, 70, or 80 miles at best, and that ran an impact car over 200 miles on a fully laden car that they gave us sort of a, what would you call it? Iris said I called it a clunker. She's being, and that is they had it so heavy with every instrumentation. I asked them why they gave us such a heavy car. They said, well, we didn't think it was going to work anyway, so what's the difference? And then it went over 200 miles, and the bells started clanging at General Motors. And there's some very good and some very smart people there, and we have an agreement with them. So now I'd like to show you their car, and it's a beauty. We do not work for General Motors. We work for all the manufacturers in the world. When we sat down to negotiate, that was one of the things that I had insisted upon, that we manufacture these batteries for everybody, anywhere. They said, Japan too? And I said, yes, Japan too. That's an impact, beautiful car. Just as fun to drive. And this gives you some idea of what's so good about it. All of you have heard the famous litany, you know. Who would want, you read mobile ads? Who would want a car, do you hear the lobbyists in California? Who would want a car that would only go 30 or 40 miles? That's like a golf cart, has no speed. You change the batteries every 10 or 15,000 miles, etc. and so on, and all that. No, they're right, very few people would want it. However, who wouldn't want a car that you could go over 200 miles, that you could go 0 to 60 in 8 seconds? These are actual figures. That you could be charged 60% in 15 minutes. That the lifetime, that the life of the battery is more than the lifetime of the car. That has benign materials in it, competitive with the gas engine. And that's just the beginning. You can look forward to more and more mileage and lower costs as time goes on. These are actual figures from actual tests, actual vehicles. So that makes the electric vehicle practical. The car that went, this electric car that went under James Warden, who was a great person, that was the first. We won the race before that at 214 miles. And then he said, oh, come on, give me a battery again next year. And that's the one he went 238 miles. The 4-passenger car that had the interior room of a Taurus. And he went 238 miles in mixed city country driving. And I think he got a speeding ticket as well. and at the same time, almost the same day, Mobile had an ad, you can't drive an electric vehicle more than 30 or 40 miles. Who is lying, and why are they lying, and what are they doing, and should we not be doing something about that? Now, this is a scooter. The movie I was going to bring would have had the scooters in there. The reason that a scooter is important is because it causes so much pollution. I won a prize in Florence, Italy, a couple years ago, first prize for the battery, and I'm walking between the hotel and the place to receive the award. I couldn't make it. I have asthma, got bronchitis, I was getting pneumonia, and I went home and had one of my colleagues pick up the prize. The scooters, as they stand there, they spew out, you know, all this, it's a 2-cycle engine, not good for you. And so we are working now in Japan and Taiwan, and of course in Europe now. These are the batteries, and they do tremendous good. They're fun to drive. They're so much cheaper than a gas engine. They're lively, and there's a great future in this kind of a battery. Those of you who saw the movie what was it? Eat, Drink, Man, Woman, or something about Taiwan. The first sight of all those scooters, 10 million of them. 10 million of them in Taiwan alone.
Yeah.
In India, there's 4 or 5 people sometimes on a scooter. The way you join the industrial society is by having scooters, because that's the only mobility that you can afford. Unfortunately, it is a terrible pollutant, and you want to do something about it. I wanted to just to, these are all the kinds of batteries in the background. There's the impact. The reason I wanted to show you that is that Bob Semple used to be chief executive, chairman, chief executive of General Motors. As I said earlier today, he's an engineer's engineer, a great leader, and a wonderful person of high integrity, and he's extremely helpful with us in our company. And I wanted to make sure that you saw him. You're going to be seeing a lot more of him. I wanted then, and I'm very serious about this, that you must have real answers to real problems, otherwise nobody will pay any attention. And so you have to be a practical revolutionary. You have to make it by making the products that prove it. And then you have to allow for a transition time while people's ideas change, where, I hate to use the term, where there's the paradigm shift that occurs. And that's what's happening. So the ups and downs, whether there'll be a mandate or not, I must tell you that with the hundreds of millions of dollars being spent by the oil companies and with the help of the big three, I think there'll be weakened mandates at best. We should not depend on mandates. We are not building our company on mandates. We're building our company to get the autos on the road so that we get the critical density and the acceleration from people who find that they now are thinking electric, because with a 15-minute recharge, with you waking up in the morning, you plug it in at night, waking up in the morning and finding that you have a full tank, with the going around and topping off everywhere you go, parking lot, parking meter, shopping center, with the idea of taking photovoltaics, not putting it on top of the car, but putting it as a canopy on roofs, as we're now doing in parts of Europe, and we'll be doing in the United States. And who's going to stop anybody from getting free gasoline, so to speak, to run your car off of the sun, which is the best place for nuclear energy, is how many million miles? 92 million miles. So, by the time people stop talking about fusion, stop talking about nuclear energy, we'll have papered the world with these kinds of products. And that takes courage, tenacity, and skill. And I want to tell you that I'm proud of the culture, I'm prouder of the culture of our company, which has such freedom and such creative people than I am of any of my inventions. And that's why we're here. We're here not because we enjoyed coming off of the plane in Europe and then coming here in tourist class so we could move on Northwest. We're here because we're part of you. Somebody said earlier to me, well, you looked at ease when you gave your talk. I said, I am because I'm among friends. I'm not here to convince you of anything. I'm here to join you in the best crusade for that better world, which is to make the world a place that we can all live in health, that we can do something about poverty, we can do something about pollution, we can do something about employment, building new industries. We can build something about the future of our children and our grandchildren. And I thank you very much for inviting us.
Well, obviously, Mr. Ovshinsky has quite a background not only in electric vehicles but also in photovoltaics. And in keeping with our conference, we decided to call it this year PVs and EVs. And the idea being that there's so much common ground here between the solar electric industry and the electric vehicle industry in terms of battery technology, battery charging technologies, solar electric, as Mr. Ovshinsky just alluded to, of charging cars, etc. Our next keynote speaker for tonight is somebody that I've been following his work for a number of years, and very proud to have him here. Somebody that's very exciting and has some the technology that promises to revolutionize the solar electric industry. And what can I say? Here he is, Dr. Alvin Marks.
I'm deeply honored to be here. Thank you very, very much for inviting me. I very much enjoyed the presentation of Dr. Ovshinsky this afternoon and again this evening. I pretty much echo his sentiments in almost every respect. And so let me carry on with what I've been doing in my own isolated corner of the world. Basically, I'm a research scientist. I have some 122 patents in various fields. I pioneered the polarized sealing, polarizing materials, super hard coatings, liquid crystal displays, 3D motion pictures, many, many things. About 12 years ago, my daughter was graduating from Smith College in Massachusetts. And during the summer, she was invited by the United Nations to be an intern there, which she did. Being a pretty intelligent girl, she was very popular. One evening, she invited me and a certain Dr. Ishrat Basmani of the United Nations to dinner. And that sort of changed the direction of my research completely. Dr. Basmani was the director of Third World Power, which uses photovoltaic systems in small villages throughout the world. And that particular evening, when we met this small Pakistani intense gentleman. He was formerly the head of the International Atomic Energy Commission, and he started the atomic energy activity and all the power supplies for Pakistan before he was driven out. But when General SEER came in and Bhutto was deposed. So at any rate, he landed up at the United Nations, and one evening I had the pleasure of meeting him. So at that particular meeting, he said to me, he said, "Alvin, you're an inventor." He said, "We have a problem." He says, my power supply system for the little villages in Africa has been denied by the UN. They will no longer fund it. It's being discontinued. I said, "Why?" He said, "It's too inefficient and too expensive." And so then he looked at me in sort of a pleading way. He says, "You know, in Africa, they're chopping down the forests, the animals are being eliminated, the desert is descending, and people are going to come into a catastrophe there. They're going to starve. The women in the villages sometimes have to travel for 12 miles or more to pick up little pieces of wood for the evening food, to cook the evening food." He said, "If you're doing anything right now," he said, "drop it, work on photovoltaics." So I then looked into it, and here I am. To complete the story, about 4 months later, I had some ideas as to how I wanted to approach the problem. I studied the efficiencies of the then existing photovoltaics. They were around 8 to 10% in that range. They were very expensive, about $5 per watt, and they were not being accepted by general utility because they were too expensive and too inefficient, just as Dr. Osmani had told me. So my background is basically, originally I was trained in graduate school in physical optics. Then I became interested in polarizing materials. I invented polarizing materials when I was 19, and I went into business on that, and throughout most of my life I've been making sheet polarizers. When you make a sheet polarizer, you take a solution of a polymer and you put iodine in it, and you stretch it, and the iodine molecules line up, and you got a lot of little conductive lines in the polymer, which basically are small antennae, all lined up. And I didn't realize exactly how it worked until during World War II, when I was a naval officer. They assigned me to Harvard and MIT, and when I was attending a class at Harvard on antenna theory, microwave, they were interested in microwaves and radar in those days. I was absolutely flabbergasted by the properties of a tiny dipole antenna, which was able to pump radiation into space and vice versa, take radiation from space and turn it into power. And then a little later on, when I became interested in this problem, I remembered back to my studies on antennae, and I came across a report by the Jet Propulsion Laboratory that they had taken antenna and diodes and were able to transmit microwave power through space at considerable distance. They were thinking about having these devices up as satellites to take sun power and pump it down to the Earth. And they were able to get 82% efficiency. I have with me the original document on that from the JPL. Well, I was very impressed by that. And then so I said, well, I know light is electromagnetic energy, and microwaves are electromagnetic energy. The principles are basically the same. Suppose I decrease the size of the antenna to the size of a wavelength of light, or a little smaller, and that would be my solution to the problem. So I would have essentially a molecular antenna diode. Now, that may sound a simple approach, but I was buoyed up in that belief by studying photosynthesis, because nature had invented this thing 2 billion years ago, before I was ever around, or any of you were ever. Every green leaf, every green algae produces, takes photons from the sun, converts the photons to electrical energy, and then performs the electrochemistry of the cell. It's electrochemical, to drive the reactions in the cell to feed the life processes. And so I knew about that. I studied that. I found that in the chlorophyll molecule there is a carotene, which is a conjugated carbon. In other words, a conductive carbon chain. In addition to that, there's a donor-acceptor complex, which will allow the electron to pass in one direction but not the other. So in the photosynthetic process, the sun takes energy from a photon from the sun and converts that electron into electrical energy, which travels down this molecular wire, and then cannot get back because it goes across molecules which permit electrons to travel only in one direction. Well, that was the basic concept. I applied for a patent on that and eventually got it. But before I got involved with the molecular concept, I had the idea of using sort of a nanotechnology to produce a submicron, essentially almost molecular wires on a glass sheet, and then coat the adjacent faces of the proximate wires. They're just like tiny antennae separated by a small space of about 25 angstroms. And you had to coat them with a donor and acceptor complex on each side. Again, easier said than done. So, anyway, I went around, I went to Cornell Nanofabrication Laboratory back about 10 years ago, and they said they couldn't do it, but there was an interesting idea. Then, strangely enough, well, I kept on developing the idea. Later on, after the war was over, under the GI Bill, I took some additional postgraduate studies. One course was in quantum mechanics, and there were many others in advanced mathematics and so forth. But when I took the course in quantum mechanics, it seemed very abstruse and not having any possible use for anything I could think of. But later on, when I started working on this down in technology, it turns out that we're down in the quantum regime. When you get to very, very small sizes, then you have to deal with quantum mechanics and not with ordinary physics. So basically, I'm a mathematical physicist. I like to try out my ideas on paper first, and then to try the experiments and make it work. I couldn't get anybody to make these things for me, but about 2 years ago, some people came into the Department of Defense, and they said they were interested in trying the idea. Turned out that they were related to a secret agency of the U.S. I won't mention the name. At any rate, totally unexpected. After 8 years of, let's say, no funds, whatever, from the U.S. government, no contracts, whatever, from it, all of a sudden, there are two major universities involved. One is Cornell, the other is Texas A&M. Texas A&M, they both wrote final reports at the end of the year. Texas A&M made the greatest progress. They reported a direct conversion of sunlight to electrical energy using the antenna diode concept. And this was partially verified by Cornell in their work. They also found strong polarization in the antenna arrays that they developed, which just as I predicted. So what I needed, basically, to do this work was a polarizing device, polarizing film, which I'll show you here, a sample of polarizing film, and the polarizing film had to be electrically conductive, and it also had to be conductive only in one direction. That was the challenge, to make such a polarizing. If you put that on, put the light on. Okay, perfect. This is a sample of the polarizing film, which we made for many, many years. This sample is probably 20 years old, but it doesn't deteriorate. Now, just like a piece of gray film, suppose I fold it over this way. It becomes opaque. Now take this film and I turn it in the other direction, it becomes transparent. That simply shows that you have two polarizers which are at right angles, and the light that goes through the first one vibrates in one particular direction. When it gets to the second film, it can't get through, it gets absorbed. However, if you put the two of them parallel, the polarization plane of both is the same, and the light will go through. To make it even simpler, I can tell you what a professor of physics told me when he was trying to explain polarization to the class. He said, suppose you have a picket fence, and you're throwing barrel hoops at it. The barrel hoops are coming in from all directions. Those barrel hoops, which are parallel to the pickets, will get through, some of them, that is. Now you take the two picket fences, you put them both in the same direction, and some of the barrel hoops will still go through. But then you stand one up on the edge, and none will get through. And that's the same principle, basically, except it's done except it's done through electromagnetics. Now, sure. Now, what was the object of this polarization idea? Well, first of all, the antenna arrays naturally polarize light. It's very strange. The polarizing light is a very, very strange phenomenon. It's actually quantum in nature. If you remember back to your physics, if you take a calcite crystal and you pass ordinary light through it, it splits up into two components. One is called the ordinary ray, the other is called the extraordinary ray. The extraordinary ray is bent a little bit away from the ordinary ray. So here you have a separation of random light, which is going in every possible direction, into two exact components at right angles to each other. And so in nature, this is a very interesting phenomenon because it seems to run contrary to the laws of thermodynamics, which says you can't take a random motion and get something regular out of it. On the other hand, with photons and polarization, that no longer applies. And the reason it no longer applies is that the laws of quantum mechanics ignore thermodynamics. So actually what happens is that energy is equal to a constant called Planck's constant times the frequency of the light. And if you sort the light out into one plane, the other plane always has to be at right angles to it. There's no in between. So that's a fact of quantum mechanics. Now, with that at hand, I knew I could get two components of light from ordinary light, and therefore I have twice as much chance of doing something with it. I could take the first component and make it travel through my conductive polarizer in one direction only, and that'll convert that particular component of the light to electrical energy. So if it were 100% efficient, you would get 50% of the energy, let's say in the X direction, and another 100% of the energy in the Y direction. Making it 50 plus 50, really. So you're getting 100%. In practice, however, a polarizer, best polarizers are about 45% transparent, which means that they're 90% efficient for one particular plane, and the other plane would be 90%. So if you could do this accurately and precisely, you would end up with a photovoltaic, which is theoretically 100% efficient, but in practice, maybe 70 or 80 if you're doing real well. And if you're not doing real well, it might be down to 10, 15, 20%, which would be great. Now, the reason why this is such a good idea, at least it was in my mind, that I've been making polarizers for 50 years, and I knew that the price of the thing was about $1 a square meter to make. Why? I can show you this again on this little piece of film. This is an ordinary piece of cellulose acetate, excuse me, I'm sorry. An ordinary piece of cellulose acetate. And try peeling up the corner of this. This is just laid on here, laid on it by electrostatic forces. Doesn't require even adhesive. There we are. I think you can see that I pulled it off. And that film, if you measure it, is a few microns thick. And the cost of the whole system, it costed out on the basis of materials and labor and whatever else, comes to about $1 a square meter. Now, two of them would be $2. You need electrodes in the system, and you add it all up about $5 a square meter. If we're really successful, we will be able to convert 250 watts per square meter from strong light from the sun. Now, low cost and easy to make, because this is a very simple process, and very cheap, non-toxic, and that was the driving force for me to work on this thing. Now, this is a diagrammatic sketch of how this works. This is the film, the active polarizing film. These are two electrodes. And this is something. These arrows indicate the molecular diodes. They're now called diodes, donor, insulator, acceptor devices. And the concept is for the sunlight to go through the system. 45% will get through and be polarized in this particular, in the E sub x direction. That's, in other words, along the x-axis. And the other will be polarized along the y-axis. And since the polarizers are nothing more or less than parallel antennae, we should get the 82% efficiency that Jet Propulsion Laboratory found of that particular vector. So we can expect maybe 45% or something like that coming out this way, 45% the other way. That would give you 90%. I don't believe we'll get there so very fast, but anyway, that's what's happening. Now I want to get back to the story. Nearly every scientist I show this to likes the idea, and eventually, after many years of publicity and patents being issued, work being done in our laboratory and so forth, we finally got a good partner in Argonne National Laboratories. Dr. Michael Wasilewski runs the photosynthesis laboratory for the DOE at Argonne Laboratory. He's a world-famous scientist in the field of photosynthesis. Got a wonderful laboratory, fantastic laboratory. And I was out there just recently during the 106-degree heat of Chicago just a few weeks ago. And we went through it and worked out to the next stage of our program. We have a contract with them. They have to spend $300,000 a year on our project, and we have to put in another $300,000. In addition to which, about the same time we had on this other project, which is parallel to this, and I'll explain that in a moment so you'll understand what went on at Cornell and Texas A&M. The two principles are basically the same. In the case of what we call a lepcon, L-E-P-C-O-N. I like to coin words because they're easy to refer to the project. The lepcon means light electric power converter. And that's basically nothing more or less than the jet propulsion system shrunk down to almost molecular size. And as I told you, there was no way of doing that until just recently. They've recently been able to get the lithographic dimensions down to about 1,000 angstroms. We really should be down to 100 angstroms or even 25 angstroms if we. And they're even getting to that point now using the atomic force microscope. So it's possible to make a demonstration of this project. So what happened basically is that the U.S. government gave two colleges, two major universities, and I might tell you a little bit about Cornell. Cornell has a center of excellence called the Nanotechnology Fabrication Laboratories, and their sole mission is to learn how to utilize nanostructures, which are extremely small structures, to be able to find out how they work on a basic level. And so they were a natural choice of the government to work on it. The other university, Texas A&M, has Dr. Bokris there, the professor of chemistry that worked with me on it, with Dr. Lin. He has vast experience in the field of lithography and electrochemistry and so forth. And they were able to do a unique job of putting together a system that was able to demonstrate the result. And as a result, we have a letter from Texas A&M stating that the thing was that for the first time, the light to electric power has been demonstrated with a antenna diode system. The next thing is that we got a letter from the project officers of these two contracts saying that they felt that the first phase was successful, and I was invited down to Houston to be on their working committee with aerospace laboratories of the nanotechnology conference, which will be appearing in October. So I'll be down there and working out how to do this on a very rapid scale. I'll get to that in a moment. Meantime, to make matters even better, suddenly we got a contract from the Air Force, which is now in effect, for working on luminoid. So we have a little money available to work on luminoid. Now I must say that while I'm telling you about all these successes, which are very nice, it's been a very difficult time for me because most of the money that's come from this thing came from a situation where we had when I started on this thing back about 12 years ago, I realized myself, my family, and my friends would not be able to fund this by ourselves. And while we approached the U.S. government, nothing was happening for one reason or another. I don't know why. But at any rate, we didn't get contracts at that time. And so we had to look to our own abilities and private investors to do it. So we founded a small public company called Phototherm Incorporated. And we have about 1,000 stockholders. And I had a very nice situation going. I had a young man by the name of Gerard Aiken, and he was really a terrific CEO and a good fundraiser, good social mixer, and he was able to get us quite a bit of money, a few $1 million. to work on the thing. However, unfortunately, after 2 years he died and with lung cancer, and the company then simply stopped functioning, and I had to take the thing over and do it on my own. So the problem right now, what I would like to do is to reconstitute the public company, and I'm going to discuss that later. But the thing is, there is a need for very substantial monies to come into this thing. Now, after my receiving the contract from the Air Force, I got another call from them to come down and give a presentation to a group at Tyndall Air Force Base at the end of this month, and with the possibility that more contracts would be let, more substantial monies would be coming in. So the thing that's held this thing up, which should have been more rapidly produced, is basically the fact that I was piddling along on a few $100,000 up to $500,000 a year. You can't do a great deal with that in research and development because people are expensive, equipment is expensive, and you get as much done as you can. However, it turned out that even though it took a long time, 12 years to get to this point, it's starting to pay off, and we're starting to get recognition from the government, and the chances are very, very, very strong that we'll be able to take off from here. Now, I'd like to go on with the technical aspect of this thing for a moment. This is the electrical structure. It's basically an interleaved grid of wires which are connected on both sides, the positive and negative. And what happens is after you make the film and stretch it out to produce the polarized, the material that you call aluminoid, the photovoltaic polarizer, just gets stretched right onto that metal grid there, which is maybe, for example, on mylar or some such backing material, and it will stay on there with just a small amount of adhesive and provide the contact between the electrodes and the film itself. So, actually, see what happens is that the current goes, let's say, outward from this particular electrode, and then downward out through here. So the current reverses between each one of these cells or strips. Next one. Yeah. This is a simplified production view the view of a production machine. Basically, what we have here is a casting belt, and the film is formed from a liquid in a trough, and it partially solidifies on the belt, gets stretched out, and then simply lies down on this conductive sheet. And that's the whole process. Is extremely simple. We have heat, drying, and so forth and so on, and maybe lamination, and that's it. So now the other thing is, okay, next point. This shows you how the two sheets there have to be two sheets in order to get the full efficiency. But you'll remember I said that the polarizing process splits the light into two components, one parallel to the sheet stretch line, the other normal to it. And so what goes through the first sheet is picked up by the second sheet, but the second sheet is turned through 90 degrees, and we can put the electrical currents from both sheets in series or in parallel, as you wish. So we get almost any voltage we want. And we can design the system so that you can produce 110 volts if you wish, or a couple thousand volts if you wish, whatever you desire. So that would be the approach. Now, I want to show a little bit on the other ones. I'm not going to show a great deal of detail on this, not because I don't want to show it to you, because it's all in patents. And I just want to simplify my talk so it doesn't become too complicated for everyone, no matter how what your background might be. But This is a diagram of a electron beam writer. What this is really a source of electrons here, and it's simply focused on a sheet here. And you can write on the sheet with the electrons, so that you can essentially use it as a pencil if you wish, to make any diagram you wish. Now, that's the next one. Yeah. For example, we might want to do this, the one on the bottom, which is a series of these in series parallel offset configuration. Simple thing to do by simply programming the beam. The next one. However, there's a catch to it. And the catch is simply that if you use a single beam, it might take you 50 years to get a square meter coated. And that won't do. So, fortunately, there is the technology has been developed, and I foresaw that about 10 years or so ago, and that in which they use sources, miniature sources of emitter sources for electrons. They even build flat screen television using 1,000 points this way and 500 points this way of emitters. 500,000. It's a huge number of from 500,000 to 1 million points on a small surface. Now, you can just as well, with the limitations of lithography, you can get 100,000 points along a meter line, another 100,000 points in the other direction, and if you multiply that out, you find that you have 10 billion points available, and that could be, in other words, you can make a pattern which is 10 billion times, made of 10 billion beams instead of just one, and that means that you can make it in 10 seconds instead of 50 years. So, looks like there were a lot of pluses and minuses. Now this shows you how the patterns are formed. If you take a sheet of glass, you can coat it with a positive ion, such as hydrogen or ammonium, or you can coat it with a negative ion, such as fluorine or some such material. Now, the trick is, instead of using a thick lithographic sheet, which they use for electron beam lithography, normally they use a polyvinyl methylmethacrylate coating, which is about 200 angstroms thick, and that means that you can't get the lines very close together. They can't be much closer than the thickness of the sheet. In this case, however, since you're dealing with a monomolecular coating or a monoatomic coating, you can get down to a few angstroms, and so you get a very accurate pattern, and that pattern can be then utilized to deposit a metal on top of it. For example, if they use a metal ion in solution, such as copper, which is positively charged, and you have a negative surface here, you can deposit just on that one surface and nowhere else. Or you could have positive and negatives next to each other, so that might even reinforce it. The pattern will be metal pattern will be deposited only on the positive charges. So in that way, you can produce instantaneously a pattern which has been preformed by 10 billion electron beams and get your very rapid reproduction. And that's, again, a very expensive scientific procedure to do this, but the thing's been laid out, it's been patented, and people think well of it. There's very, very much more to tell, but I understand I'm out of time. And it was really my pleasure to be able to present this to you. And I hope that you'll find it interesting. And my point of this whole thing is to change your thinking, to realize that new technology can come along and produce a more efficient, lower cost photovoltaic for your utilization in industry and by the public at large. Thank you.
And actually, Larry Spring, could you come up also? I have the real pleasure tonight. We decided that with this wonderful group of people together, that we couldn't pass up the opportunity to make an award. And in addition to these two wonderful gentlemen, we have our own local inventor, Mr. Larry Spring here, who's been out front. Larry's done a lot of similar work to these two gentlemen, and I'm sure you saw his devices out front. And it's our pleasure tonight to present all three of these gentlemen with the Renewable Energy Development Institute Lifetime Achievement Award for 1995. Let's have an acceptance speech from Larry real quick. You haven't had a chance to talk. Think about all this.
I live over in Fort Bragg. Lived there for quite a few years. I lived on planet Earth for almost 80 years. So I've gone to the school of life for a long time. And I was a high school graduate. So I sometimes say, well, I'm a high school graduate. I think of all the years I've spent learning since then, it adds a lot to your knowledge. I come upon some very interesting things rather recently, and I tell people, if you haven't arrived at this point yet and understand what I'm saying, I didn't get there till I was over 70 years old, so you still have a chance. I come upon some very interesting observations of transmission of energy, and it comes directly from experimentation. So it should, every time you put it to the test, it should prove itself to be correct. It doesn't necessarily dispute the books, but it doesn't necessarily coincide with them either, because they've learned it different ways than I did. I learned this all hands-on by working with antennas, and I was in the television business for about 14 years. And then I found myself sitting at a bench till 1 o'clock in the morning working out problems underneath the television sets. And I decided that maybe I could do a little better to real estate because things were moving really good. Instead of getting out 10-cent resistors from a television, I was getting out $1,000 commissions from property, which give me enough resources to actually be able to give away a lot of the knowledge I'm getting now. And so I've written up several books, and I combined them, 5 books into one single book, which is a large book I call Common Sense Physics. And then I extracted from that a small booklet, which is only 102 pages. The reason it's 102 pages is I want to staple it. I want to get out of reasonable. So I could give it away without giving away all that much money. And so these little booklets, they cost me a little bit, but I want everybody to have one. Not because I want you to realize that because I'm giving it to you, that it isn't a cheap book. It has probably more information in here on electromagnetic energy than any book ever published. And because it comes directly from experimentation. And so you'll find a lot of material in here. So don't consider this as a cheap book because we're going to give everybody here a book. you haven't already got one out front there. And if you don't see any interest in it yourself, there's always somebody, a neighbor or a friend or a relative or some young fellow that really benefits by this material. So don't let it sit on the shelf, move it around, and this is the best way we get this information out. Because I set up a little school over there in Fort Bragg where I take little people through in small groups and really let them understand it. And they all keep nodding their head the right way, and others going this way. And so when you're out in the field of discovery, you have no fears for what you're doing. If I was to ask the status quo if I was right at what I was doing, they had not learned it that way. And so they would automatically give me a bad rating on what I'm doing. So I just am like electrical current. I take the line of least resistance. I go to the people that are thinking along these terms. And this little booklet here is called Magnospheres and the Spring Atom. Now, these little radiated energy units are spherical in shape, and they are magnetic in nature, and they have magnetic force, just like you find between two magnets. But they're driven off from an alternating current, and so they come out in little spherical units. And if they weren't spherical, the satellite dish wouldn't work. So first thing you have to recognize is they're spherical in shape. Then the next thing you want to know is how large are they, which you can readily determine, just like screening gravel through screens. If you hold the screen up there, it'll either go through or they'll bounce off of it, depending on the size of the openings. That determines what's transparent and what's not transparent. So then you find there's a whole lot of other things that take place. One of the things is that the energy units have to have a surface about the size of the unit to be a good reflecting surface. And this is something we ran down last winter and put it in this book. So that is out beyond my original large book, which I call Common Sense Physics. So I want you all to be brought up to date with what I'm doing, and this book will do that. And I'm happy to give it to you, and I appreciate all the smiling faces that are giving me encouragement here. Before you leave, we want you to get the book. Now, what's the
They can just come up and get one right here.
Okay, they're right here. You're welcome to them.
I'll get you one.
And take one for family, or if you have some friends, take another one.
I have to read another.